After we have incorporated all the loads, we will run the finite element analysis. You will show some kind of straining flexural actions like this. This is a tank. On both sides, there are irrigation tank with two chambers. This is a raft foundation. So we will always work with axis. This is showing you flexural movement in one direction. And it is showing you intensity also. So you can check all the contours of flexural straining actions, and you can check in SAP 2000 or any finite element software how much reinforcement you need to provide from this. This is for walls. This is in vertical direction. If walls are like this, there is nothing. So M22 is usually the vertical direction axis. So vertical direction will govern. This is a typical example of vertical direction movement in tanks. This is same irrigation tank just to show you how flexural stresses and flexural movement can be seen in SAP 2000 for design of walls. This is same clarifier again. Now this is an existing clarifier from physical pictures, planning design. Then again, why I am showing you this picture, you can see there is scrubber and scummer on the top. On the left, you can see this is taking everything on the top, and it will be taking it here in the next picture. Here, there is a weir on the left. This is again where interdisciplinary coordination will come. This all sewage water from clarifier, which has come and scrubbed from there, it will move out down in the conical section, and the clean water will go from the weirs to the next secondary or tertiary process. So you will be needing what type of weir you need and clarifiers. If you will zoom out, if you will carefully look both of these pictures, you can see there are cracks developed on the tank walls because this tank is not designed from ACI 350-06, which has stringent criteria. This tank was designed and constructed back in 1994. After this, it started developing cracks. So because the durability is very important, that I'll tell you next slide, the crack has been sealed many times. That is why the importance of crack mitigation and appearance comes for design of rectangular structures. This is the most important thing for design. Durability, resistance to corrosion, deterioration due to fumes or chemical attacks. Most important are all these things, stability and durability. This is a typical cross-section of a wall where you can see both sides of reinforcement has been utilized. On the tension side and on the compression side, both sides are utilized to calculate the crack width. Now here comes, this is ACI 224R, control of cracking in concrete structures. If you will see at the bottom row, can you check this is only 0.1 millimeter allowable crack width. If you will see dry air, you have crack width 0.41. If you have seawater in your structure, it's 0.15. If you have humid soil around your structure, still you can go for 0.3. But when it is water retaining structure, you need water tightness, you need durability, you need tight appearance criteria so the cracks will not appear as I shown you earlier in clarified. So we will go always for 0.1 millimeter. This is very stringent criteria because this needs hefty amount from government. So water and sewage should not leak from this structure. It will, the cracks will open up with the passage of time. It will harm the durability of the structure. This is equation from ACA 350-06, and on the right is Appendix C of same ACA 350-06 code. Now, in the previous codes before 05, ACA used to calculate a factor Z, which is on the right side. This is a factor to quantify and distribute the reinforcement. But when they extensively checked the structure by their laboratories in America, they found out that, like I showed you the clarifier, it is designed from this Z factor, kip per inch, how much kip per inch, how to quantify reinforcement and distribute them on tension side. The people were using this till ACA 350-06 didn't come. Now ACA 350-06 wants to limit severe exposure different and normal environmental exposure is different. And it is limitizing two things. One is allowable stress in your steel reinforcement. If you'll see 10.6.4.1, this equation is to calculate allowable stress for normal exposure. 10.5 is for severe exposure. It depends on how much sulfate are attacking your structure from your soil and water, how much is the pH value of the fuel of the liquid that your structure is carrying. Both these things are very important. There is another equation in AC 350 that will tell you how to calculate durability factor, not to impose any strength cracking limit state also, strength limit states also. Let's move on to instability of underground structures. As I told you, buoyancy is the most important thing which will uplift your structure, especially if this is very light structure. If you'll see a wall chamber or a box which is 5 by 5 only, you will see what is this structure, why we are going into so much stringent criteria. But I have literally seen tank floating above the ground because the designer did not take into account properly the buoyancy effect. That's why we always play with the weight of the structure. We always provide some overhangs to give the stability to the structure. So that if there is enough reinforcement, but structure is uplifted, so what is the use of the structure? All the hefty amount has been wasted. So the most important thing when all you guys will be working on underground structure is stability other than cracking. It should not uplift because of buoyancy effects. Now I'll go to a little introduction to elevated tanks. On the left, you can see we have two types of tank. On the left, you can see this is a tank in Saudi Arabia, elevated tank, only supported on shaft. It is somewhat like a mushroom. And on the right is typical structures in Southeast Asia and even here. This is staging. The staging is good on the right structure. The framing is good. They have better dissipations. But on the left, the structure looks good. It looks more contemporary structure. And it also depends on what type of soil you are encountering there. The main difference will be the primary forces from underground tanks and elevated tanks. Underground tanks are not subjected to so much severity of seismic loading, because even if the load will come from the left, you have the soil on the right. So your structure will be hardly move, or your structure will be stable. It is a confined structure. But when you have so much elevated structure, which is about 40 meters tall, and it is standing only on one shaft, that's where you have to play with your loading. It will be subjected to high wind loading. There is no wind loading on underground tanks. It will be subjected to water loading. It will be subjected to hydrodynamic forces. This is very crucial topics in design of elevated tanks, and normal seismic forces will come here. Now, what is the difference between overhead tanks and underground tanks? That I have already tell you. Overhead tanks are subjected to hydrodynamic forces, wind loading. They have larger temperature forces, so we have to go for some lethargic and laborious temperature gradients and temperature loading. Underground tanks are somewhat different. They are subjected to groundwater, sulfates attack, pH value is different, but they are not sensitive to seismic loading. This is a hydrodynamic forces development of a mechanical analog model. The process started in 1963. Husner was the one who started to model and analyze the structure which has elevated tank, how to check the liquid in the tank actually, how to model the mass in the tank. That is more important, because the mass in tank will have two components other than the normal load, which you will not have in other building structures. That is called impulsive and convective components. You can see this is a spring model. The tank liquid has been modeled as impulsive MI, and the tank slushing component has been modeled as convective component. So I'll be telling you on the next slide what are they. Here we go. These are the components of hydrodynamic forces. This on the right you can see there is an elevated tank. This elevated tank has staging, which is called HT, which is at the base of tank. How much is the height of your columns? At the down is you have foundation thickness. When the seismic force will come in any elevated tank, there will be some portion of the water which will try to move with the tank wall. It will be supposedly rigidly connected with the wall. So we call it as impulsive component of the tank. On the left, there is wall distribution for model. So when we will make this in any finite element software model, the wall will have three types of loading rather than one type of seismic loading. This wall have mass. Because of this mass, seismic force will be acted on this wall. Other than this, there is liquid which is resting on this wall on the right. So this liquid will try to move with the wall. On the left side, you will see this is the value of impulsive forces are maximum at the bottom of wall because they are trying to move with the wall. They are almost rigidly connected with the wall. In the next picture, which is in the middle, you will see there is a diagram which is showing the pressure distribution is maximum on the top. This is where the convective components come. If you will put water in your jug, when you will try to move, you will see slushing will come on the top. This is the slushing components. Other than the component of water which will try to move with the wall, maximum pressure will be on the top. When we will try to design a overhead tank, we will try to add all these inertial forces due to wall and tank, convective forces due to this, and there is lateral distribution of water. So all these things will be there and we will add up and the pressure distribution diagram will come like this. Maximum wave of water we can have. We have maximum height of tank. We'll detect the freeboard from this. We'll get how much maximum oscillation wave can come on this tank. Now we will move on to tank foundation for steel welded storage tanks. This is another course. I forgot to tell you all these criteria mostly for API or elevated tanks. They have been taken from PIP, process industry practices. If you will read any literature on the internet or any international code, you will see they will be referring to things. API, American Petroleum Institute, 650 is the code to design the foundation for welded steel storage tanks. PIP STE, PIP STE 03020. This is a code to design the foundation for process industry. We can have fuel tanks, we can have fuel tanks. So process industry requirements are mentioned in PIP, Process Industry Practices Structural Guidelines 03020. And API, American Petroleum Institute 650, design of foundation, tank foundation for welded storage tanks. On the left, you can see there is an elevated tank. This is a welded elevated tank. Other than elevated tanks like concrete tanks, for these light structures, steel tank structures, generally we go for ring type of foundation. You can see on the left picture, there are two types of beams. This is called ring foundation. Because the welded storage tank is light, it is steel, because you are not providing any footing inside the tank. You are trying to economize the structure. API 650 tells us if the tank dia is less than 20 meters, we should go for ring foundation in order to economize our materials and construction. Same is for height of tank. If our tank is more than 20 meters in height and in dia, we will go for raft foundation. Why? Because this ring foundation on the right is the forces acting on this ring foundation. This has been taken from API. You will see a shell steel structure connecting to this ring. You have to follow the vendor guidelines. How much will be the thickness of shell? What should be the minimum width of the ring foundation? And more importantly, we always try to ignore the passive pressure on the left. This is as per code also, because maybe passive pressure might not have been developed due to the construction sequence. So we always neglect the shear resistance in calculating the width and size of ring foundation, and we calculate the passive resistance which is been on the left due to passive resistance of soil. Other than this thing, you will see a plate above this ring. This is usually called annular plate. Below annular plate, sometimes we are providing protection boards also. And below this, you will see compacted clean sands. So we have foundation only on left and right, going circumferentially. And inside the tank, we don't have anything. We have only coarse sand or gravels to drain this element. But when the tank size is big, the soil is very susceptible to any kind of differential settlement or any kind of other loadings, or your size of tank is big, or the ring foundation is subjected to too much twisting moment. We call it torsion. So too much torsion is bringing the size of the ring beam such a big that the small tanks shall be designed for a raft rather than a ring foundation. The saving and the durability will be more in raft foundation. Now, if you will have big load, the same slushing equipment will also come on the foundation. There will be base shear due to inertial load. there will be base shear due to slushing load, there will be base shear due to impulsive load. These all will come on your foundation. So when the tank is big, there is too much seismic load and their soil is very bad. So nobody will go for ring foundation. They will always go to have something which is good solution. Now you can see a 13 thick asphalt impregnated board is provided below sometimes this tank. This is for enhancing the durability of your foundation. These are the minimum requirements. From finished grade level, you should provide at least 6 inches your ring foundation higher. As you can see, you need something above the top of your berm. And there is 2 feet. All the codes are in American FPS units, but we can calculate these things to SI units after we have finalized. All American codes are in not in SI units, in FPS US customer units. In the right picture, you can see the top of berm should be at least E. This value in the code is at least 6 inches. So other than the analysis and design, when we will be designing a ring foundation or a raft foundation, first we'll be needing the vendor directions or vendor inputs or vendor requirements. How much he will make away this shell on the ring foundation? How much should be the top of the berm? What is the minimum size of foundation we'll be needing from geotechnical report? What should be minimum width of berm? Minimum width of your ring foundation? What should be minimum embedment of width foundation? So serviceability criteria is again will be governing all of your tank foundation. This is how we are proceeding in tank foundation. Here is how you can grow up in a career path. I'm sure most of the things I have shown you today might not have seen you in your career earlier. How the clarifiers work, how the API tells you what should be the requirements. So when you will be going into the drilling of international requirements for environmental structures, you will be more proficient first as an engineer, as a civil and structural engineer. You can work alone as a consultant. If someone is sending you, I need this clarifier, I need this tank, you will be better telling them as a consultant how to work. You can have jobs in water supply and infrastructure projects. You can have job in waste treatment plants, in Ministry of Waters. And more important, I'm sure you will have more things how to collaborate with electrical, with mechanical and process supply whenever we are going for any sewage or wastewater treatment plants. These are the references, as I mentioned, most of them earlier. Code requirements for environmental engineering structures, ACA 350-06. Minimum design loads for building and structures, ASC 705. The minimum crack width requirements as per control of cracking in concrete structures, ACA 224R. And wherever the pictures I have taken from somewhere, I have enlisted them down. The most important for fuel tanks, APA 650, welded tanks for oil storage, and process industries practices, structural engineering 03020, process industry practices for tank foundations.